Okay, I think we're ready to go. So it is wonderful to be here. First of all, it's great to be here to celebrate Doug's 66th birthday. It's also great for me personally to be here because not only did I do my PhD at Toronto, I did my undergraduate degree at Toronto, but I have something even more unique than that. I went to high school at the University of Toronto. So I've been on this campus off and on since 1965, and it's wonderful to be back. So what I'm going to try and do today is, first of all, to say happy birthday to Doug. So I've got two things it says here: a celebrated mathematician and a renowned computer scientist. One of my pet peeves for a long time has been many of my colleagues, many of my graduate students would look at this and say, well, which one is he? Is he a renowned computer scientist, or is he a famous mathematician? Because you can't be that great at both. And every time someone says that to me, I say, go and look at Doug Stinson's record. Because if there's ever been someone who exemplifies top of the field in computer science, top of the field in mathematics, I always use Doug as my exemplar for that category. So happy birthday, Doug. What I'm going to try and do today is I'm going to try and tell you about a whole class of problems, and towards the end, make some comments about what I think about some of the solution strategies and what we should all be thinking about when we're using them. So the generic setting here is you have a number of data items of some kind. There's some finite set of data items, and you're going to replicate the items. You're going to make a number of copies of them. You've also got a finite set of locations in which you can put these items. But right away, you can guess that you don't want any location to get overloaded with items or any item to get too many replications. So for load balancing criteria, we're going to insist that each item be stored at least some number of times. And of course, not too many more times than that, because we don't want to waste the storage we have. And every location should have approximately the same number of items. But more than that, we're going to ask that if I look at two different locations and look at the items they share, that number shouldn't be any larger than it needs to be. And if I look at two different items and look at the locations they share, that shouldn't be any larger than it needs to be. So there's a lot of problems of this type. And not surprisingly, when you go to get away from data items and storage locations and just abstract this, you say, well, I'm interested in certain set systems. So we're going to be interested in set systems that are uniform, finite collection of points or elements, a collection of subsets of those elements called blocks typically, but we're going to be asking that it's uniform in the sense that all of the blocks have the same size. We're also usually going to be insisting on regularity, that every item appears in the same number of blocks. It has the same replication number. Now, of course, most of the people in the room will know right away that there's a very important class of regular uniform set systems that have even more balance. They're called Steiner systems. So I've written a strange definition of Steiner system here, trying to use the vernacular of regular uniform set systems. But really the defining property is that if you take any T set of elements, you find exactly one block that contains it. Now, I was thinking that for those of you who don't know much about Steiner systems, I really should spend some time talking about the importance of Steiner systems and where they show up. But I thought, even for the people who don't know, this might be interesting. Steiner systems have applications that are far beyond anything you might expect, right? So who would have thought that Steiner systems would be crucial in, for example, waste disposal? So if you it's unfortunate. This company is a German company and they went out of business. So this is now an impossible slide to get on the internet anymore. But needless to say, these are not the kinds of Steiner systems I'm talking about. So what next then? We focused in regular uniform set systems, impact Steiner systems. But now we're free to choose the assignment of data items to storage locations. So that means we're free to choose the incidence matrix of the Steiner system that we're going to use. That's going to give us specific assignment of data items to storage units. So generically, I could say I want a Steiner system, but now I'm asking for a total ordering on the points of the Steiner system and a total ordering on the blocks of the Steiner system in order to determine what the assignment is. And then the question is, well, why didn't I say that at the beginning? Is there any reason I might prefer one incidence matrix over another incidence matrix? And so it turns out that there are some very good reasons for that. It could be that not all of the items are homogeneous. It could be that not all of the storage locations have the same access rate, for example. It could be that different storage locations have different access mechanisms. I may prefer to have certain data items on certain storage locations. And sometimes I may need to recover from errors that arise. So I may need to ensure that I can do error recovery as well. Well, how might these affect? Well, for example, if they affect the access times to the data on the storage locations, then I might prefer one incidence matrix over another. And so that's a general area called access balancing. Now, let's just throw out a whole bunch of them. So let's look at a V by V incidence matrix. So points by blocks incidence matrix for some regular uniform set system. Now, if I take a particular block, okay, so a particular column, I can look at where the ones are in that column. And if I produce a sorted list of the row indices where I find a 1 in that column, I'm going to find k different locations, k different rows where that column arises. And now I can start, so I'm going to produce that in sorted order. And now I can say, well, what kinds of things might I look at? Well, I might look at the first row in which it appears, the last row in which it appears, the difference between the last and the first. But also things like, if I look at consecutive appearances, so it appears in block 3 and in block 7, I can look at the separation between those. So separation and spread measure how spread out those point indices are. And the last one on the list says, well, I might want to look at something like the average of the point indices contained in that block. So that way, instead of just looking at one of them or a difference between two of them, I might look at the average of all of them. Well, I haven't said average here, I've said sum instead, but of course, because we're talking about k things in each block, whether I talk about average or sum is not really going to matter. Now, this tiny little picture at the bottom that you can probably barely see is a picture of a book by Dewar and Stevens called Ordering Block Designs. So the reason I put that little picture there is to remind everyone that this is a small fraction of the kinds of things you might look at in order to order block designs. And data item storage locations is one instance of many different reasons you might want to order block designs. So if you're looking for more of these, look at the Dewar-Stevens book. It's an excellent introduction to this. Okay, well, now I've listed a bunch of things: start, stop, span, sep, spread, sum, I confess they don't all start with S. I artificially changed the names to force them all to start with S. But they're reasonable names. Once you've done that, you can look at block metrics across the whole array now. And so what I could do is I could say, well, let me calculate that metric for each of the blocks and then take the maximum or take the minimum. Well, or take the average of them. So once I think about average, then I could take the variance of them. How spread out are they? But the other thing I might look at is the difference to try and balance. Okay, so difference is about balancing things, making sure two things don't get very different metrics. Two blocks are as similar as they can be. And ratio is a multiplicative way of accomplishing the same thing. And then our goal now is, having chosen some block metric and some array block metric, we want to determine how we should permute the rows to either maximize or minimize one of those possible array block metrics. And then if that's not enough, I mean, I keep compounding the number of problems we could look at. If I haven't mentioned enough, of course, I'm still talking about doing this for one regular uniform set system, or I could just tell you the parameters of the regular uniform set system and say, you get to pick the system. Then you get to pick the ordering for the array block metric you're after. Now, okay, so I probably like inundated you with possible things you might look at, but now I'm going to double it. Because it makes perfect sense, of course, to say, well, if I have an incidence matrix, I can transpose the incidence matrix, form the dual set system, and then the block metrics become the point metrics of the dual. So I could equally well talk now about ordering the blocks, labeling the blocks, and looking at point metrics. And these all make perfect sense as well. So you get a whole parallel set of problems for the point metrics. Now, you might say, well, okay, big list of problems, so what? Well, some of these problems have been studied pretty extensively. So maximizing the minimum block span, this is a problem that I think Brian Alsbach set the ball rolling on it. Don Crayer got involved, then Doug got involved, and there's been a lot of work on these good sequences or good sequencings or block avoiding point sequencings. And recently there's been a beautiful paper by Daniel Horsley and Porig Okathine, in which they make big inroads in this problem. This turns out to be one of the problems of this type. Something like minimizing the maximum block start sounds like a strange question, but it turns out to be the same question as saying, find me a largest independent set. Minimizing the maximum point start turns out to be finding a largest partial parallel class. Well, what about maximizing the minimum point spread? So now we're saying we're going to look at how close together two things can be and then try and push them as far apart as possible. This turns out to be a problem that I studied with Myra Cohen starting in about 1999, and there's been some extensive work on it. There we had the clever and meaningful name of pessimal, worst possible labellings, which seemed good at the time, but hasn't stood up, I think, well to choice of vernacular as time has gone on. So I'm not going to talk about any of these. I said I was going to talk about popularity, so let me fit popularity into this framework. Well, items have different popularities. Think about files. Most files, so if you look at something like MapReduce or Hadoop file system or something like that, most files actually never get accessed. It's depressing, but files are generated and then never accessed. And There are some very popular files. There are some files of intermediate popularity. There are some files that are not popular at all. So we should take that into account. But also storage locations are not homogeneous necessarily. So we may have that certain storage locations are more desirable for one reason or another. And if I'm stuck with having 5 copies of my file put out in this file system, I don't want to be put in all the bad places. I want to be with some of the cool kids, right? I mean, I want to be in the right place, at least some of the time. So Dow and Milankovitch in 2018 wrote a paper in SciM Journal on Discrete Mathematics where they identified these problems with popularity, pointed out that dealing with actual popularities is really difficult. So what they suggested is, well, let's rank the items by popularity, rank the locations by desirability, and instead of worrying about the actual numerical values for popularity, let's just use the ranks. And once they did that, they said, well, now rank is just the labeling, the point labeling I've assigned, or the block labeling that I've assigned. So it's just the index of the block or the index of the point. And then looking at, the popularity of an item amounts to just looking at the sum metrics. So the sum metrics that I put at the end of my earlier list, these now show up as popularities. Okay, so a block sum then is the sum of the point ranks of the points in the block, and a point sum dually is just the total or the sum of the block ranks of the blocks containing the point. And what should we be after? Well, we don't want any individual sum to be too small. So what are we asking for then? Well, in the framework we talked about before, we're saying, let's maximize the minimum block sum. And that's called the min sum problem. I also don't want any block sum or any point sum to be too large. So then I want to minimize the maximum of the block sums. And that's the max sum problem. But really, if what I'm after is access balancing, what I want is I don't want the sum for one point to be really different from the sum for another point, or the sum for one block to be really different from the sum for another block. And those are the difference sum or diff sum problems. Now, I'm going to try and narrow in because I let it get too big and out of control. So I'm going to focus on max sum, min sum, diff sum. But there is some work done on ratio sum, and there's some really beautiful work done by Gudian Ge and 2 of his colleagues on the variance sum as well. Okay, well, so I better start making things a little bit more concrete for all the people who I've lost. And you can jettison all the stuff about the generality if you're trying to just figure out what the heck is he talking about. So here is a Steiner quadruple system of order 10. So it should have 10 rows. Those are the 10 points of the system. It should have 30 columns. Those are the 30 blocks of the system. And this is an incidence matrix for it. And now, what am I doing to get the sums? Well, the first thing I might do is I might say, well, look at that first column. If you look at that first column, you see it has ones in positions 0, 1, 2, and 3. Add those up, that gives you 6. That is the column with the smallest sum. And so the min sum here is 6. The max sum here is 30. And I can calculate now, because I'm looking at a specific incidence matrix, that the diff sum between the largest and the smallest is 24. When I do the opposite and I look at the rows now, the min sum for the transpose matrix, which is just really saying I'm looking at the rows now, is 86. The max sum's 262, and the diff sum's 176. So you can go through and do these calculations. I don't suggest you do it. First of all, you might discover that I made a mistake, and I don't want you to do that. But on top of that, I don't think it's particularly instructive. What you really should be asking yourself is, well, is that kind of balanced? Is that a good solution? And I guess you can probably tell right away that's not a particularly good solution. So here's another. You can see that the min sum here has gone from 6 up to 11, and the max sums come from 30 down to 25. So we got a diff sum now of 14. You might say, is that the best you can do? And by computer, not by brilliance, but by computer, I know that that is the best diff sum you can get, even though it's not the best min sum you can get, and it's not the best max sum you can get. Okay, so that may sound a little bit surprising. You may have to pay a price. If you insist on increasing the min sum, you may be forced to increase the max sum as well. So that's kind of instructive that I went from a diff sum of 24 down to 14, but I really am in this example stuck there. But what's really striking here is look at what happened in the dual. Look at what happened with the row sums instead. Minimum is the same as the maximum. It's 174. This is perfectly balanced. The diff sum is 0. I was shocked when I first saw this. I did not think this was going to happen. I've been working on the point versions of the problems for quite some time, and I did not expect that the block versions were going to look so totally different. But here you see that, I seem to be stuck with a pretty significant diff sum for looking at the column sums, but the block sums, I was able to balance it perfectly. So now, I mean, we've got one example. I can calculate the sum metrics for a specific incidence matrix very easily, but what I'd like to do is to even know, how do I find the ordering that gives me the best metrics? How do I sequence the points? How do I sequence the blocks to get these values in general? I do not know an efficient algorithm to do that. I would be very interested in knowing how to do that in general. But what's even more important probably is, once I've decided what I'm trying to do, instead of just asking about, here's a specific incidence matrix, can I now, over a family of set systems of some kind, can I optimize these metrics? So first of all, I told you I was cutting you down to 3 problems. I'm going to try and cut you down to 2 now to save you a little bit of work. So the first thing you might notice is that if you have an incidence matrix and you just flip it left for right, flip it top for bottom, so reverse it in both directions, you can calculate the max sum of the reversal from the min sum of the original, and vice versa. So in fact, if I guarantee to you that this incidence matrix has the best possible min sum, its reversal has the best possible max sum. So what that means is that now, instead of worrying about min sum and max sum, I can say, okay, I'm going to pick min sum. I'm going to focus on min sum. I'm not going to worry about max sum, because to get from max sum to min sum or back is just a matter of reversal. And a lot of people say, well, but that's great, because now you can eliminate diff sum as well, because after all, diff sum is just max sum minus min sum. So please be careful, okay? Why am I telling you to be careful? Well, diff sum is max sum minus min sum for a specific incidence matrix. But that's not even the case for a specific set system, because different labelings, the one that gives you best min sum may not give you best max sum, okay? Okay, so let's jump in and see what we can say. So the first question you might ask is, well, how bad might things get? Why don't I just be random? You know, just see what happens if I just write down an incidence matrix. Well, if you've got a Steiner system that has two disjoint blocks, of course, I could label the points in one block with all the smallest labels, label the points in the disjoint block with all the largest labels, and that's going to give me the worst min sum, the worst back sum, and the worst block diff sum. So similarly, if I try and do that for points, it almost is the same, but now I need to be careful because if I try and label all the blocks containing a particular point with the numbers from 0 up to the replication number -1, I can do that. Or I can label them all with the largest labels, but I can't do both simultaneously. So this is a case where for diff sum, I have to worry about if I take a pair of points, how many blocks are they in together, okay? And so that's going to make a small adjustment, and diff sum is not going to be quite the same as saying max sum minus min sum. Now, I don't think anybody would ever use a labeling like this, so you might say, can we look at how well we might be able to do from the other end? Well, let's start off. We've got a regular set system. We know now, if it's a regular uniform set system, we know that in such a regular uniform set system, B times K is V times R. So we can calculate the total block sum because we know how many ones there are in each row, right? And so we can now calculate a total of all of the block sums, divide by B to get the average block sum. And you get this very nice looking quantity. A half of K times V minus 1 tells you what the average block sum must be. Well, of course, now that's the average, so it is an upper bound on the block min sum, and it's a lower bound on the block max sum. So this tells us something about what our target might be that we're looking for. And I don't want to belabor it, but of course, the dual gives you the same thing. The only thing you might jump in and notice is that now it's this expression, a half R times B minus 1. Not a surprise. Should be exactly what you expect. And now you've got an upper bound on the point min sum and a lower bound on the point max sum. So for points, those bounds I just gave you are going to be pretty useful, but for blocks, what we're going to find is that actually there are better bounds that are going to rule out the possibility of getting perfect balance. So let's take a Steiner system, an STKV Steiner system. We know what its average block sum is. So let's now look at the first T minus 1 points. Form the derived system with respect to those T minus 1 points. So we started off with a Steiner system with strength T. We've derived with respect to T minus 1 points. We now have a Steiner system with T equal 1. So what is a Steiner system with T equal 1? Well, it's just a partition of a set, okay? But now what I know is if I look at that partition that I get, every block in that partition has size K minus T plus 1. And we know how many blocks there are in that partition, but now we know what the average block sum of a block in that partition is, because we can just sum up all the numbers from T minus 1 up to V minus 1, divide by the number of blocks, and that gives us the average block sum of those blocks in the partition. And so you get this expression, T minus 1 choose 2 plus a product here. But let me just say what this gives you in terms of consequences. So here, oh, that's very nice. So here you can see that the difference between the max sum and the min sum is a fairly significant amount, right? K minus 1 times V over 2, K plus 1 times V over 2, and the diff sum is bounded below by a linear quantity for t equal 2. For t equal 3, it's still a linear quantity, but now it's doubled, then tripled, and this pattern continues. So the diff sums you're going to expect are going to depend on the V, of course, but also on T and K. I'm not saying that these can be realized. What I'm saying is that nothing better than this can happen. Okay. So what do we know at this point about what's going on with block metrics? Well, there's a paper here with more initials than I can count, but the first author is sitting right there, Yaoming Chi. I'm the second author. Then let me see if I can get all of the others. Dow, Gabris, Ling, Lucy, and Milankovitch. Okay, so after this, I'm probably going to call it the 7-author paper. So in that 7-author paper, one of the things we noticed is that actually, if you've got a Steiner system that has a small maximum independent set, it must have very large diff sum. So in fact, if you take, say, even Steiner triple systems, and you look at what kind of bound you might get on the block min sum for the worst possible system, because Steiner triple systems exist that have maximum independent sets of size no larger than root v log v, that's also a bound on the best min sum you might get. Use reversal to get the best max sum, and you can see that the best diff sum is actually very large. It's very close to the worst that could happen to you. So that's a kind of depressing result in a way, but on the positive side, Dow and Milankovitch showed that you can get a Steiner triple system with min sum equal to V, and they proved that you can't do any better than that for Steiner triple systems. They asked the question, what can you do if it's a Kirkman triple system instead? And my PhD student Dylan Lucy and I recently showed that at least when B is 9 mod 18, you can get a Kirkman triple system with that min sum as well. But notice I've backed off and I've started talking about min sum when I said what I really wanted was good diff sums. So what can we say about diff sum? Well, Dow and Milankovitch showed that the diff sum has to be at least B, but in the 7-author paper, we showed that except when B is 7 or 9, it has to be at least V plus 1. And using the Schreiber-Wilson construction, we were able to show that for all orders, it doesn't need to be any bigger than V plus 7. So we've got it bracketed now, V plus 1, V plus 7. What the truth is in between that, I wish I knew, okay? So it seems like a pretty small gap that should be able to be closed, but we don't have really a good idea how to do that right now. So for Steiner quadruple systems, actually there's one very nice construction, just the doubling construction for Steiner quadruple systems shows that the Boolean Steiner quadruple systems realize with equality the best bounds, which is kind of a striking result. It's a very thin infinite class, powers of 2. But nevertheless, it really tells you that, you know, maybe for Steiner quadruple systems, one can say a lot more. For S24Bs, Dylan Lucy has done quite a bit of work using the tripling construction, but no matter how much effort he's put into it, he's still epsilon away from getting anything that will match the bound. So I think for blocks, we need a lot of work. And I got this email a few weeks ago when I was making up my slides for the Italian conference, actually, and I liked it so much, not just because it made me feel important that my input makes a difference, but that they knew my name so well. So personalized email. So here's a personalized email that I will share with you that your input also makes a difference. right? So points. Well, points were in much better shape. So I'm going to approach this fairly obliquely by starting with the worst things I can do. So the worst thing that can happen to me, the largest point diff sum I could possibly get grows like b to the power 2t minus 1. And you might say, well, but only a crazy person would do that. So use randomness. So if you just choose a random block labeling and you say, I don't know anything about the labeling at all, then using Chebyshev's inequality and the union bound, you can drop that immediately quite substantially from 2t minus 1 in the exponent to 3t over 2. Now, let's use just a weensy little bit of design theory. So suppose this can be partitioned into alpha parallel classes. Okay, so I'm going to assume there's some decomposition of this into alpha parallel classes for some fixed alpha. And now all I'm going to do is I'm going to randomly order the first alpha parallel class, randomly order the second, randomly order the third, but I'm going to glue them together consecutively. That idea alone, no change in the probabilistic machinery, Chebyshev's inequality and the union bound drops you down to b to the t. Now, you can do better. If you say, I was looking for these alpha resolvable things, and all I could find was a whole bunch of stuff about resolvable designs. Even better, alpha is 1. Well, if you now have a partition into parallel classes, you can not just use Chebyshev's inequality, you can use Chernoff bounds. And if you use Chernoff bounds, you drop this now to an even better exponent, t plus 1 over 2, but the price you have to pay is this extra log v term. And so you might, if you were of a probabilistic inclination, say, I'm going to keep going in this direction. Look at how much of an improvement I'm getting. But I don't want to encourage you to do that, because I think that you could continue to squeeze more and more and more out of this without discovering the truth. I think the truth is that for these point problems, the truth should be that you can perfectly balance when it's numerically possible to do so, and the problem is large enough. So in other words, an STKV with B blocks and replication R could have point diff sum as small as 0. Now we know from the conditions we calculated earlier that that can only happen if either the number of blocks is odd or the replication number is even. So I'm going to give those things a special name, egalitarian. And if you say, show me an egalitarian system, I'm going to say, I already did. Because that S3410 that we looked at earlier, that's precisely what we did, is we produced an egalitarian labeling for it. Well, if you can't get an egalitarian labeling, what's the problem? The problem is that the average, when you divide by the number of points, it's not an integer, it's a half integer. Well, that means the best you could hope to do is to get them to differ by 1. So let's call that almost egalitarian. Well, let's start off really easy. The S22V. Now you might go, 2V, blocks of size 2? I remember Jeff made a joke years ago that somebody said at a talk something about they were stuck on t equals 2, and Jeff said, well, I'm stuck on k equals 2. So here's a problem with k equals 2. So what is this S22V? It's the complete graph. Okay, so when you look at the necessary conditions, it says it could be egalitarian when b is 1, 2, or 3 mod 4. It could be almost egalitarian when b is a multiple of 4. And it turns out that with 2 exceptions, namely with the exceptions 4 and 5, that condition is sufficient. Most of that work was done in a paper already in 1967. The almost egalitarian is somewhat more recent. So let's move up one. Steiner triple systems. Steiner triple systems, I wrote a paper in DCC about 2 years ago that shows many constructions and infinite classes for egalitarian Steiner triple systems. In that case, because the replication numbers are always going to be odd, because so the necessary conditions there say there could always be an egalitarian system. And the data I have suggests that they do exist whenever v is greater than or equal to 13, but there's some congruence classes that are still problematic. For Steiner quadruple systems, the doubling construction again turns out to be really useful. When v is 420 mod 24, you can start off with an ingredient that's not egalitarian, but the doubling construction has this lovely property that it not only doubles the system, it orders it too. So you can actually make egalitarian systems from ones that aren't, which is something that, again, surprised me a little bit. And when v is 8 or 16 mod 24, you can always make an almost egalitarian system. This kills half the orders, but the other half, all I have is a little bit of computational evidence that shows that, yeah, the answer should still be yes, but I really don't have a strategy for how to prove that. Well, let's go to larger block size instead. So S24V, S25V, and so on. Well, there, Marco Berardi and a cast of many people has worked over the years on one rotational resolvable difference families. And they give substantial number of examples of egalitarian systems for S2KVs with various values of K. So there's a lot done here. It seems reasonable at this point to ask the question, if I fix a T and a K, do egalitarian or almost egalitarian systems exist, except when V is small? And I don't know any values of T and K where I can prove that there are infinite classes of systems that are not egalitarian or almost egalitarian. So I kind of feel like here I'm looking for one, but they seem so common. Everything I try seems to find one. That doesn't mean I can prove anything about it, but it does mean that it seems curious that I also can't find out what the obstacle is that would prevent me from finding one. So it's conceivable that maybe everything is egalitarian once it's big enough. Do not quote me on that, okay? I mean, I know you're recording me, but don't quote me on it. I did not express an opinion about it, okay? So if it turns out to be true, you can say, yeah, Colbourn had this real insight and saw that that might be true and suggested that people look at it. But if it's wrong, then it was like Colbourn suggested it, but he never thought it was true. Okay, we understand how this works? Okay. I want to tell you one result. So this has nothing to do with defense. So this is an asymptotic existence result. It shows that if you take the necessary conditions for the existence of an egalitarian S2KB, they're listed here. So the first two are just the standard existence for the S2KB itself. The last conditions required for it to be egalitarian, that this condition is asymptotically sufficient. And I'm not going to prove this, but I am going to try and give you a quick outline of how it works. So I'm going to make a bunch of graphs at the beginning. The first class of graphs I'm going to make, they're going to have even replication number and an even number of blocks. But the key property is that they not only can be decomposed into cliques of size K so that those cliques of size K have an egalitarian ordering, but it has one more property. What is the extra property? It's a property called being split. Split means if I take my egalitarian ordering, even number of blocks, cut it in half, look for how many times a point occurs in the first half and the second half. I want them to be the same for every point. So split egalitarian ordering. If you can do that for these graphs, then I'm going to include a finite number of those in my collection. So that's first type of ingredients. Second type of ingredients. Now I'm going to be looking for odd replication number, an odd number of blocks. But now I'm going to ask for a different condition. Again, I want the ingredient to be taken apart in a way that's egalitarian. But I want it to be resolvable. And I want the egalitarian ordering to look like parallel class, parallel class, parallel class, strung out that way. So when I was typing the slides, I had this parallel egalitarian, but somehow I was typing quickly and it became paralegal. So this is now a paralegal labeling. I got to tell a story about a paper that Jeff and Doug and I worked on. We have been working on these things on thwarts in transversal designs. And I don't know which one of us did it, but somebody was typing very quickly and the paper was tentatively titled "More on Thwarts." But when I saw the draft, it actually said "More on Thwarts." So, so that's what it was called internally for quite some time. So here, you might say, well, how are you going to make these things? Well, for both for the split and for the paralegal, you can make them from doubly resolvable transversal designs. But here, there's this really rich class of them that come again from this class of one rotational resolvable S2KVs that Barati and his colleagues have studied. Now, some graphs of the first type, one graph, not some, one graph of the second type. I got a collection of graphs. I want to take a huge complete graph and partition it into copies of these graphs. And Lamkin-Wilson does this, right? So the Lamkin-Wilson existence result for graph designs tells me that I can do this. And so now what I do is I just apply Lamkin-Wilson. I only use graphs of the first type unless I need the graph of the second type, but I can calculate when. So I'm going to have this graph design with just graphs of the first type, or a graph design with graphs of the first type and copies of that single graph of the second type. And now you say, okay, but you've totally lost the ordering, but you can get it back. So in the 7-author paper, we showed that you can partition. We showed that for the one design, you can always do the partition if the class sizes are even or the number of classes is odd. And it turns out here that that is precisely what we need to take all of the copies of that second ingredient, the paralegal one, and interleave them to get an egalitarian labeling for all of the graphs of the second type. Okay. I put a footnote here because you have to be a little bit careful. I'm not guaranteeing in these intermediate things that I'm talking about set systems that have the same replication numbers anymore. So I need to be careful to make sure I have the definition of egalitarian right. But that's a technicality. What do you do with the graphs of the second type? Of the first type? Well, take one of them. What is it? It's a split egalitarian. Well, it was called split egalitarian for a reason. What should you want to do with a split egalitarian system? Split it. Put the first half at the top, second half at the bottom, and just keep doing it, growing the egalitarian labeling both directions. And when you finish, you've got some details to check, but you have built an overall egalitarian labeling. So that's as much of the proof as I'm going to say. This almost works for almost egalitarian labelings, but it doesn't quite, because that interleaving doesn't give you a difference of 1 anymore. So I'm hoping that this can be repaired for almost egalitarian systems as well, but I don't know at this point. For t greater than 2, of course, then I lose the Lamkin-Wilson result. And there's a ton of stuff recently with Kivash, Kuhn, Osthaus, and others. I don't see any result there right now, that would give me the machinery I need to handle higher T by the same mechanism. It may exist. If so, I don't know it. I want to repeat this question that even this theorem says that there is one, probably says there's lots actually, but it certainly doesn't answer the question for me, are most or all of them egalitarian when they can be? Now, another thing I really want to spend a little bit of time on is I could now stand up and say, I have solved the existence question for egalitarian S2KVs. And so have I, or what exactly have I done? Well, if I have a disk storage application and somebody says, what I need is I need a Steiner triple system on 67 points, that's egalitarian. Well, 67 turns out to be the first open order right now, where we don't know an egalitarian system. 103 is the next one. We know almost all the small orders, but those two were missing. So I go and ask my asymptotic friend, and my asymptotic friend looks at me and says, no problem, these all exist. Egalitarian Steiner triple systems exist. And so every time I hear this, I can hear in my brain the line from the movie Cool Hand Luke, what we have here is a failure to communicate. So my first inclination is to say, they're not listening and they don't understand what I'm after. But I would encourage you not to say, that's irrelevant, what they just told me. Quite often, the probabilistic methods do tell you whether or not the design might exist. Some constructive techniques you might use to try and find a solution, perhaps some way to formulate the problem or decompose the problem that might be useful even for small examples. So in our situation, paralegal and split labelings turn out to be something that, I mean, they show up very much in trying to get the asymptotic method to work, but they're also very good machinery for trying to build small examples. So I'm hoping that this communication between the two sides of this street doesn't break completely. I think that both sides have a lot to tell people on the other side, and and I think that some of the techniques that are developed in the asymptotic world are definitely going to be useful for us. So summing up, it's a pun, sorry. So there's lots and lots and lots of open problems on block sums, even for Steiner triple systems. I don't know what the answer is exactly. I would love to know even an infinite class of Steiner triple systems where it's like, that is the answer and here's why. For point sums, lots more is known, but despite that, the spectrum for Steiner triple systems is not completed, for Steiner quadruple systems is not completed, for Steiner S24V systems is barely started. And I know it was weeks ago that I was telling you about span, SEP, spread, and a whole bunch of other things. So what happened to all of those? Well, I think there are a lot of problems there. And if you dig into those literatures, they tend to have gone in different directions. And I feel like there's some room for unification here. So I have three more things to say, and all three are going to be quick, okay? So the first thing I have to say is that please do come at 5 o'clock today for the ICA medal presentations. I want to give you a puzzle and a piece of advice for the coffee break, okay? So first, the puzzle. So one of these people is not the same as the other people, and you can probably find many differences, but there is one very significant difference between one of the people in this picture and the other 5. So I will leave you to figure that out. These were all 6 editors-in-chief of the Journal of Combinatorial Designs, including Doug, up to, I guess, 2018. Jonathan Jedwab has joined since, but naturally isn't in the picture. So that's the puzzle I want to leave with you. And now, finally, I think I still have a minute, a piece of advice.